Hello everyone and welcome back to another deep dive. Today we're going back to school, specifically to the chemistry lab.
Oh, the lab.
I want you to just visualize a scene that usually causes a lot of anxiety during the practical exams.
Ah, the practicals. The external examiner is watching you, right?
Exactly. You're standing there holding a test tube.
Oh,
Inside you have that classic light blue solution of copper 2 sulfate.
I've all seen it.
That nice gentle blue. The examiner looks at you and says, add some ammonia. So you pour it in and suddenly, boom.
Magic happens.
It doesn't just dilute. It turns into this intense, deep, dark blue color. It's stunning. And then the examiner asks the dreaded question, why? And usually this is where students just freeze. They know a reaction happened, but they can't explain the structure behind it.
It is a classic, vivid observation. But in chemistry, especially for the board exams, magic doesn't get you marks. Structure gets you marks. And that brings us to our topic today, Werner's theory of coordination compounds from Unit 5.
Unit 5, coordination compounds. Listen, if you are looking at the previous year's board papers, this chapter is a goldmine. You cannot afford to mess this one up. It carries a lot of weight.
It does. And Werner's theory is the foundation. Without this, the rest of the chapter, it makes no sense. See that color change you described?
Yeah.
It isn't random. Werner's theory explains why metals form these specific, stable recipes that don't fall apart.
So without this theory, we basically can't tell the difference between a complex coordination compound and just a simple salt.
Precisely. Before Alfred Werner came along, chemists were completely confused. They would mix things like cobalt chloride and ammonia, and they would get results that just defied the rules of simple ionic chemistry.
Right.
Werner gave us the hidden rules. He showed us the structure.
Okay, let's crack this open. I'm going to play the role of the student who is revising for the exam but keeps getting confused between all these terms.
Good idea.
Let's start with the absolute zero-level explanation. What is the core idea Werner proposed?
At the simplest level, Alfred Werner proposed something that was, well, revolutionary for his time. He said that metal atoms are special.
Okay.
They don't just form one type of bond. They possess two types of valencies or, bonding capabilities.
Two types. Okay, usually we just think of one valency, like carbon has valency 4.
Yeah.
But here we have two.
Correct. He called them primary valency and secondary valency.
Let's break them down because I know definitions are asked directly. What is primary valency?
The primary valency is what you already know from basic redox chapters. It is ionic. It corresponds to the oxidation state.
Right.
And ideally, it is satisfied by negative ions.
Okay, so that's the charge valence. That's the plus and minus attraction. If the metal is +3, it needs -3 to balance it. Simple.
Exactly. But then comes the twist, the secondary valency.
The game changer.
Yes. The secondary valency corresponds to the coordination number. These are satisfied by neutral molecules or even negative ions. But here is the key.
What's that?
These are coordinate covalent bonds, and they are directional.
Directional. That means they point somewhere specific in space.
Correct. They lock the groups into a fixed geometric arrangement around the metal.
Okay, I want to pause here. Before we go deeper, I need to make sure we have the anchor definition for the exam. If the question asks, define a coordination compound, what do we write?
Okay, good point. Here is the definition you should memorize. Coordination compounds are formed when ligands donate electron pairs to form coordinate covalent bonds with a central metal atom, resulting in a complex ion with a specific geometry.
That is a dense sentence. Ligands donate electron pairs. Let's visualize what is really happening at the particle level, because definitions are hard to remember if you can't see the picture.
Okay, imagine the metal atom, say cobalt, is just sitting there. It has these empty spaces, which are basically empty orbitals.
Right.
Now, the ligands, these are molecules like ammonia or chloride ions, are drifting nearby. They act as Lewis bases. They are donating pairs of electrons into those empty spaces on the metal.
So the metal is receiving these electrons.
Yes. But here is the most common confusion point. Host. If a metal has a charge of +3, how many things do you think it attracts?
Well, logically, if it's +3, it should attract 3 negative things, right, to balance the charge.
And that is exactly where students lose marks. That is the #1 misunderstanding trigger. You are confusing oxidation state with coordination number.
The primary with the secondary.
Exactly.
Okay, so fix this for us. Why is that wrong?
Because they are independent properties. Primary valency is about charge. Yes, it needs to balance the +3. But secondary valency is about, let's say, seating capacity. It is about how many ligands can actually bond and stick to the metal physically.
So a metal can have a +3 charge, but it might want to bond to, say, 6 things.
Exactly. It implies that while the charge balance needs 3 negative ions, the spatial arrangement, the secondary valency, might require 6 groups to be attached. The charge is one thing, the structure is another.
That is a huge distinction. I feel like we need a really solid analogy to keep this straight in our heads.
Yep.
In our notes, we have the parking lot analogy.
Yes, let's use that one. The parking lot analogy is perfect for understanding the coordination number.
Okay, I'm listening.
Imagine the central metal atom is a building, and surrounding this building, there is a private parking lot.
Okay. A building with a parking lot.
Now, this parking lot has a fixed number of spaces painted on the ground. Let's say there are exactly 6 spots.
6 spots. Got it.
This number 6 is the coordination number. It is the secondary valency.
Right.
Now, the cars driving around are the ligands. They want to park. The secondary valency is satisfied when all the spots are full.
Okay.
Once that lot is full, once you have 6 cars parked, no more cars can enter.
Even if there are 100 cars waiting outside.
Even if there are 1,000, you cannot force a 7th car into a 6-car lot. This explains why we get specific formulas. The metal has a fixed seating capacity.
That makes so much sense. But what about the primary valency in this analogy? The charge.
You can think of the primary valency as the entrance fee, or the bill that needs to be paid.
Okay.
The ions that satisfy the primary valency might be just hanging around outside the parking lot, just balancing the books, but they aren't necessarily parked in the spots.
Okay, so some ions are parked inside, satisfying the secondary valency, and some are just floating outside, handling the money, the primary valency.
Exactly. Sometimes an ion can do both, pay the fee and take a spot. But we will get to that. The key is structure, parking spots, is different from charge fee.
This is so important, and this leads to the proof, right?
Yeah.
How did Werner actually solve this? There was that puzzle with the chloride ions.
Yes, this is where he proved the theory. It's all about precipitation.
Right, the silver nitrate test. Walk us through this.
Okay. Imagine you have 2 beakers. Both contain compounds made of cobalt, ammonia, and chloride. They look similar. But Werner added silver nitrate, agnoia, to both.
And we know silver nitrate reacts with chloride to form that white precipitate of silver chloride, AgCl.
Correct. But here was the shocker. In the first beaker, he got a massive amount of white precipitate. It turns out all 3 chloride ions reacted.
Okay, as you'd expect.
But in the second beaker, same elements, mind you, he got much less precipitate. Only 2 chlorides reacted. The third one, it just ignored the silver nitrate.
Wait, how can a chloride ion just ignore a reaction? Chemistry is chemistry, isn't it?
That is exactly what people asked, and Werner said the chloride didn't react because it was locked inside.
Locked inside the parking lot.
Exactly. In the first beaker, the chlorides were only satisfying the primary valency. They were outside the coordination sphere. They were ionizable, they were free to react.
And in the second beaker?
In the second beaker, one of the chlorides had moved inside the coordination sphere. It was acting as a ligand. It was parked in one of the 6 spots. Once it is satisfying the secondary valency, it is strongly bonded. It is non-ionizable. It won't break away to form a precipitate.
That is brilliant. So the chemical test literally tells you who is inside the house and who is standing outside.
Yes. Primary valency is ionizable outside. Secondary valency is non-ionizable inside. That differentiation is why he won the Nobel Prize. He proved that molecules have a 3D structure.
That is the aha moment. So when we see a formula with those square brackets like CONH, the stuff inside the bracket is the parking lot.
You got it. The square bracket is the coordination sphere. Nothing leaves that sphere easily.
Okay, let's do a mental movie to lock this image in. I want everyone listening to take a second. Close your eyes if you can. We're going to build one of these compounds in our minds.
Let's do it. Picture a glowing metal ion, let's say iron 3, Fe, just floating in the dark space of a solution.
Okay.
It is glowing, maybe a faint yellow, and it has empty hands, these are its empty orbitals, reaching out into space.
I see the glowing iron. It has hands reaching out.
Now imagine neutral molecules like water or ammonia drifting closer. These are the ligands, and they are carrying gifts.
The gifts are the electron pairs.
Yes. As they drift closer, they place these gifts into the metal's empty hands, and the moment they do snap, the hands close.
Like the lock.
Like a lock. They are now fixed. They don't move randomly. They arrange themselves in a perfect shape, usually an octahedron.
A specific geometric shape.
Yes. The ligands are now part of the metal's identity. And because of this specific arrangement, The way that glowing center interacts with light changes. The color shifts.
That is a beautiful image, and it connects right back to our first question about the copper sulfate.
It does. Let's revisit that.
So in the intro, we had light blue copper sulfate. We added ammonia, and it turned deep blue. Using this whole picture, what actually happened?
Originally, the copper ion had water molecules parked in its spots. That arrangement reflects light blue.
Okay, so the parking lot is full of water cars.
Right. But then you pour in ammonia. Ammonia is a stronger ligand. It's like a luxury car that really wants that spot.
And it kicks the water out.
It pushes them out, yes. It's a substitution. Now, the parking lot is full of ammonia cars. The structure is now satisfied by ammonia.
And because the partners changed, the energy levels changed, and boom, deep blue color.
Exactly. The metal didn't change. Copper is still copper, but the coordination environment changed completely.
That is so cool. But let's raise the stakes. We always ask, why do we care? Besides passing the exam, does this theory apply to anything? Life or death?
Oh, absolutely. Let's talk about something scary. Cyanide poisoning.
Okay. That's definitely high stakes.
We know cyanide is deadly, but the mechanism is pure coordination chemistry. Cyanide is a very, very strong ligand. It attacks an enzyme in your body called cytochrome S oxidase.
What does that enzyme do?
It helps your cells make energy. The cyanide bonds to the iron in that enzyme and just blocks it. It shuts down your body's power plant.
That sounds terrifying. So is there an antidote?
There is, and it uses Werner's principles. The antidote is a form of vitamin B12 called hydroxycobalamin, and this molecule contains cobalt.
Cobalt again.
Yes, and here's the trick. The cobalt in the antidote offers a better parking spot for the cyanide.
Better than the enzyme.
Much better. The cyanide leaves your enzyme and rushes to bond with the cobalt in the antidote. It forms a stable complex which your body can then just safely excrete.
That is incredible. So the antidote works by providing a more attractive parking spot for the poison.
Exactly. It's a ligand exchange reaction saving a life.
Wow. Okay, I have one more example here labeled counterintuitive. This is for the students who try to use simple logic and fall into a trap.
Yes. This is where you lose marks if you aren't careful.
So here's the student logic. Cobalt has a +3 charge. Therefore, it should bond to 3 negative things, like Kukli.
Sounds logical, right?
It sounds logical if you stop at primary valency, but the reality is different. Cobalt actually forms compounds like coclum and cocleo.
Whoa, wait. That's 5 ammonias and 1 chloride. That's 6 things total attached to the metal.
Correct.
But the charge is only +3.
And that is the point. The cobalt bonds to 6 things because its secondary valency, its coordination number, is 6. It doesn't care that ammonia is neutral. It just needs to fill those 6 parking spots. So it fills the geometry first.
Yes. Think of it this way. The metal has a frantic need to fill its geometry. That's the secondary valency. The charge balance, the primary valency, is just the accounting that happens afterwards.
Primary pays the bill, secondary bills the house.
That is a fantastic way to remember it. Primary deals with the electrical bill, the charge. Secondary builds the physical house, the structure.
Okay, we are approaching the end. I want to make sure the students listening have their cheat codes ready. These are the exam-safe clarity lines. Can you walk us through them?
All right, let's go through the key takeaways for the board exam.
Number 1.
Coordination number is independent of oxidation state.
Tie that back for us.
This means just because a metal is +3, do not assume it bonds to only 3 things. It usually wants 4 or 6 ligands. Don't mix them up.
Got it. Number 2.
Coordinate bonds are covalent.
Why is this important?
Because students sometimes call them ionic. No. The ligand gives both electrons, but once that bond is formed, it is a shared directional bond. Do not call it ionic.
Number 3.
Geometry is fixed.
Meaning?
Ligands do not dance around randomly. They sit in a specific 3D shape. If the exam asks you to draw the structure, draw a proper octahedron or tetrahedron.
Right.
The angles matter.
Finally.
Number 4.
Charge versus structure.
Butt down one last time.
Primary valence determines the charge. It's ionizable. Secondary valence determines the structure. It's non-ionizable. Keep those 2 jobs separate in your head.
Awesome. Okay, let's wrap this up with a short summary for revision. If you zoned out, come back to us now.
Okay, first, the core idea. Werner discovered metals have 2 valencies. Primary is about charge, and secondary is about shape.
Second, the analogy.
Think of the parking lot. The metal has a fixed number of spaces. And remember the silver nitrate test? Only the ions outside the parking lot will react.
Third, the real world.
The color change in copper sulfate is just cars swapping places in the parking lot. And the cyanide antidote works because cobalt offers a better parking spot for the toxin.
And the final reminder. Never, ever confuse the charge with the number of attached groups. Oxidation state is not coordination number.
You know, hearing all this, it really shifts your perspective. We usually obsess over the formulas. Is it Co? Is it Fe? But Werner showed us that how they are arranged is just as important.
It is. In coordination chemistry, geometry is destiny.
Geometry is destiny. That's a powerful thought. If simply changing the arrangement can change the color or turn a poison into a cure, structure really is everything.
Indeed, it controls the function completely.
All right, that is it for our deep dive into Werner's theory. Go crush those board exams. Don't let the confusion between primary and secondary valency trip you up.
Clear concepts lead to full marks. All the best for your studies.
See you in the next one.